bottom. Expect. I'm going to stir that up, unstir it, and I'm going to slowly remove this to the way. Can you give me a piece of that paper? Can you see what's happening over there? Sorry, Pete.
No, you're all right. Okay.
So what's happened so far? Has it gone across the top?
Yes.
And has it hit the side here?
Yeah.
What's happening now?
It's going down.
Oh, it's going down.
Going down.
That's what you said, Alex.
Mm.
Right. Is it still going down? Oh, right. What's it doing now?
It's going back up.
Oh, it's going back up again. So where's it going now? Oh, going back across the top.
Yeah, go back to the top.
Oh, right. Why do you think this is?
It's still hot, isn't it?
Because it's hot. So you're saying it's, and what if it's hot? What does that change? And why does it rise?
More buoyant.
It's more buoyant. And what if we want to say that in technical terms? What do we?
Has a lower density.
It's density. We're looking at something that's dense, and it looks to me as though it's gone all the way across there, and then it's probably bouncing back again. Is it?
So
It's hitting the
No.
If it's hitting a barrier, so
it's just being forced down. Because it can't go off. It can't
So-
go anywhere
It
else.
can't go anywhere else because it's got momentum. It's got
Momentum.
somewhere. And as it goes down, the buoyancy overcomes the effect of the momentum on the way down, and makes it go back up.
So we have a red layer at the top, do we? So you'll find it relatively easy, I hope, to think about what's going to happen. Now you might be thinking, can you hear the ice in there? You might be thinking I'm a tricky person, so this might not actually be cold. It might not actually be blue if I can't take the top off. I'm going to colour it blue. So, is it cold?
Yes.
It is cold. So let's have a look.
You put the white to the behind.
What about your idea, Dom?
Garbage.
What about your
Another brilliant idea.
what about your idea, Bavlina? All right. Did it hit the sides?
Yeah. But it's not
Right.
gone down yet. It's still going up.
Oh, it's still going up.
Yes.
Okay.
Lava lamp is saying yes.
Right.
That's a
S-
convection
s-
thing,
s-
isn't it?
Still going up.
No, it's gone back down.
Oh, right. What's it happening to it now?
It's going back down.
Oh, it's going back again. Okay, so am I right in thinking, because I can't see from here, that we've got a red layer at the top, a colourless layer in the middle, and a blue layer at the bottom?
It's brown
Cool.
now.
That's good. That's patriotic. Okay, so now you've seen how it works. So now you'll find it very easy, unless you happen to be the people who did this morning, in which case say nothing, please. What I'm going to do now is I'm going to do exactly the same thing with some milk. So I'm going to put this in here. I'm going to put the similar amount of milk in, I'm going to stir it, I'm going to unstir it, I'm going to lift it out in exactly the same way. And if you saw what happened this morning, to say nothing, and if you didn't, have a talk to the people around you.
We did it.
Same thing, milk. This is what, semi-skimmed UHT milk, is it?
Yeah.
All that might be important.
oh,
gone under the blue?
Yep.
Yeah.
So what?
Actually, was
It
right.
was
What's happening to it now?
Looks like it's sinking. Oh, no.
It's taking over.
Wow.
Did,
No, it's definitely
did
pushing
it did
blue
it
up.
bounce up here?
Yeah.
Came up.
It has
And-
pushed blue up.
And it's bouncing.
But
off
now
the
it's
other
going
side
up.
now.
It's pulling the red down.
Oh, it is.
Oh, on the other side, yeah, because it's going up that way. So,
It's pulling the red down.
well, it will, because if it's pushing it up there, it's making, it's physically making space. So it has to. Something has to fill that space.
So, you've seen what happened. It actually went along the bottom even faster than the blue stuff. Why do you think it moved faster?
How come the fat isn't floating?
Denser.
Well, that was a distractor from me. It's because milk is an emulsion, and the fat is an emulsion, and it actually acts like particles rather than separating fat and so on. But nevertheless, that was good
So
thinking.
will that be faster with full fat milk and slower with skimmed milk?
Doesn't make any difference.
It won't make any difference.
Doesn't make any
Not
difference
enough to make
at
a
all.
difference.
So am I right in thinking that we've got a red layer at the top, a colourless layer, a blue layer, and a white layer?
Yeah.
Fantastic. Because you thought that this was a fish tank. This is not just a fish tank. This is the world's oceans. What you saw when the red stuff went across the top is what we see in the Atlantic when we get warm red currents going across the top, called
Oh no.
not in the Atlantic.
Atlantic is
Gulf Stream.
Gulf Stream.
It's the Gulf Stream which becomes the North Atlantic Drift. That's how that moves. If it happens in the Pacific Ocean from time to time, it is the El Nino effect. So you have seen how you get warm water going across the top of oceans. But of course in oceans we sometimes get cold water, particularly at the Arctic and Antarctic. What happens to cold water currents? You've seen what happens to them. They go down and they go across the ocean floor. And what happens to them then? Well, they hit the sides eventually. And what happens then? They upswell. And what happens then? They bring lots of nutrients and thousands of fish. And this is where the big fishing areas are on Earth. So this is how the oceans work. Do we get things like the milk? Well, geologists, we do, don't we? And what do we call that? Because 3 of you looked at that this morning.
Oh, was that mudslides or slopes?
This is a turbidity current. It starts off, you say, as you say, a mudslide or slope. These go down. What happens if you're not familiar with this is you get sand and mud building over the continental shelf. You get an earthquake, usually loosens that, goes shooting down and covers thousands of square kilometres of ocean floor, producing a sequence that grades up from the bottom that somebody called this morning a Boomer or Baumer sequence. And that's what it is. You have just seen a turbidity current. In fact, you've just seen 3 turbidity currents, because turbidity currents just mean it's material of different densities.
So it doesn't have to be the sediment.
It doesn't, because it is sediment in oceans, but it can be other things. So this is a model of the oceans. It's a model of lakes, because the same thing happens in lakes as well. It's also a model of the atmosphere, because what happens when you get hot air in the atmosphere?
Rises.
It rises, and then where does it go? It spills across the top of the atmosphere. When it rises, is it pressing down on the ground less hard or more hard?
Less hard, so it's low
It's
pressure.
going up, so it's low pressure. So you've seen what happens in cyclones. Low pressure, the material rises and it spills across the top of the atmosphere. What happens when stuff in the atmosphere gets really cold? It goes down. Does that press more on the ground? It does. What do we call that? That's high pressure.
Anticyclone.
So when high pressure gets to the ground, what happens to it? Well, it spills
Spreads
across the
sideways.
ground. What do we call air spilling across the ground?
Wind.
Wind. This is wind. This is what drives the systems on Earth. And did when
Thank God you're sat down, puppy.
I'm just going to leave now.
when you saw the blue thing going across here, that was a cold front. A cold front is cold air moving along, pushing the warm air out of the way. Do we get things like the milk in the atmosphere? Yes, we do. When you saw the Twin Towers collapse on the telly, you saw huge eddies of dust. That was a density current of dust in the air.
Is that the same
Avalanches?
as when the volcano
Exactly the same as a volcano.
Yeah.
If we get white hot ash coming down a volcano, we call that a nuée ardente. If you get snow and ice buoyed up in air and sliding down hillsides, we call that an avalanche. And what you know, it's one of these things because it just doesn't go down the valley and like that. It goes down the valley and bounces backwards and forwards, just in the same way that you've seen here. Have you seen a nuclear explosion on the telly?
Oh yeah, it bellows out.
It goes
Goes
up
up and
and you get the
bellows
mushroom. At the bottom, you get the base surge. That's what kills people. Mostly within 25, 30 kilometres, they don't have to worry about anything. Don't have to worry about radiation because and that's a density current as well. So this is not just the ocean, not just a fish tank, it's not just the atmosphere. Actually, what happens with solid material? Does solid material move?
Yeah,
Oh, right, okay. So if you get hot solid material,
the mantle.
where does that stay?
It rises.
It's-
No.
it stays,
Hot
stays
solid material. Why is it?
solid, and it can flow. It stays at the top. If you've got solid material that's really cold and really dense, what happens to that?
Sinks.
Well, it goes down. What do we call that?
Subduction.
Subduction. So you've just seen a model here of subduction. This cold, dense material going down. So this is not just water, it's wind, it's solid material. And if we now go on to this, in what we've just done here, did you see me do any concrete preparation? What was the concrete
Yeah, you showed
preparation?
us all the bits and what you were going to do.
I didn't actually tell you what these things were at all. I asked you to tell me. Tank, water. I modelled what I was going to do. So that was the concrete preparation. Was there any construction in what we just did? Was there a pattern? What was the pattern?
Do you want me to do the red, then the blue?
You did them in a particular order.
So there was a density pattern, wasn't there? Was there any cognitive conflict?
Yeah.
You didn't know what was going to happen to the mill, did you?
Hypotheses were all
They all behave differently.
They're all over the place.
They could have been modified, they could have been improved. Metacognition, well, that's what we're talking about now. Did we do any bridging? Taking this learning and applying it to new contexts?
A lot of British.
Well, this humble fish tank is the whole solid, liquid and gaseous earth. So I think there's a bit of bridging in there, isn't there? So that's how to teach a case lesson. And it's really great because you were really, really watching this. And this shows the power of prediction in science teaching. Because if you ask people to predict what's going to happen, three things happen. One, they watch much, much more carefully. I could have heard a pin drop when you were watching what happened. And if I'd just done it, you probably wouldn't have done that. But because I've done it and we made predictions and you had a personal investment in it, you were watching much more carefully. We've also used that. Prediction involves teaching thinking skills because this is what case does. And it's also what scientists do. Because scientists make predictions and they test them and they get them wrong sometimes and then they retest them. Have we just been doing science? Good, okay. Well, that was that